a little bit of review on this. That reminds me, there should have been a whole slide. Maybe it's going to follow this with vocabulary words. Maybe I put it out of order. We use latitude and longitude to give us positions in the sky. What is latitude? Okay. Lines of latitude are obviously related to the word latitude. What I'm looking for here is not the line.
Is it north and south? East and north? Just kidding.
Okay. The latitude is the measurement of how far you are north or south. Okay. And so because they're measurements of how far you are north or south, and the lines run east to west in circles around the earth. And so I was trying to avoid confusion. That's why I'm only talking about your latitude instead of talking about the lines of latitude. So the latitude is how far north or south you are of the equator. What is the equivalent we use in the sky for that? Starts with D.
Declination.
Declination.
There you go. Displacement.
Declination. Wrong class. So declination is exactly equivalent to latitude. There is no difference. So whatever is your zenith in the sky is at its declination is your latitude. There's no difference. And by the way, after we finished lab at 11 last night, you know what the sky was? Clear. The app eventually got there. It's just ahead of its time. Okay, longitude then is how we measure east to west from the prime meridian. And so the prime meridian goes, where does it go through?
Somewhere in
The Royal Greenwich Observatory, which I put my definitions in between this and the next slide that has the picture of the prime meridian. Good job. Let's go over these words before I forget them. Just want to make sure we have. What does conjunction mean?
It's like opposite from you.
Opposition is opposite from you. Or opposite from the sun, excuse me. In the same side of you as the sun in a straight line. That's what conjunction means.
So conjunction, sorry, I'm thinking of lab, how there was like a planet somewhere there in the sun, and if it would have been on the other side, then it would have been conjunction, so then that confuses me now.
Okay, so I totally wish that it would take my writing, but my working hypothesis that we worked out, Leslie, you were part of this. I'll give you that kind of credit. I'm going to try one last time. This pin is lit up. Come on. Ah! God bless. Okay, I've got to show you now. Told you. See all that scribble there that we couldn't see? Yeah, it was recording it. Okay, so here's the sun at the center, and we have one orbit, and then let's make another. Excellent. Make another orbit that is like this. And so if you are on this planet and you see, changing colors is not super convenient, and you see this planet here, then that is going to be a conjunction because it's along this line. It's a superior conjunction because it's the farther of the two possible conjunctions. So that's a superior conjunction. The inferior conjunction is on that same line, but it's the closer of the two. It's the one that's on the side before you get to the sun instead of the side after you get to the sun.
So I just remember there being that line, that six, the six of that line or whatever.
Mm-hmm.
What is that line?
Well, that was just a line connecting the sun to the planets when they were in a lined up configuration. They were either opposition or inferior conjunction, depending on which planet you're on.
So a conjunction is when they're on the same side as the sun? Or
Yes.
Wait, that kind of confuses me because the sun's like a circle, isn't it?
Well, we're going around the sun.
Yeah,
We're on the circle.
yeah.
And so, because we're all going around the sun at different speeds, the times when they line up are the only times that these
Oh,
apply
when the
to.
planets line, like the two of them line up like those.
Yeah.
Like,
So these are
oh.
only specific times when they're going to line up when these words apply. And so when the red planet's here, the purple planet says that's a superior conjunction. When the red planet's here, we say, well, that's nothing special. When the red planet's here, we say that's an inferior conjunction. What's a superior planet versus an inferior planet?
The ones.
Inferiors are closer to the sun, superiors are farther from the sun. It's not a statement of value. It's not like if we say, well, person A has a superior intellect and person B has an inferior intellect. That would be bad or good. Here it's just farther or closer. Quadrature. What's that crazy quadrature? When you have a right angle in the planet-sun configuration. And it doesn't matter if you're on the red planet or the purple planet, that's still quadrature because that's the only configuration you can get between the planets to have the right angle. Okay, vocab done. Now we're back to the prime meridian. Now, as I was reading this, how many people have read Dan Brown's The Da Vinci Code? The Da Vinci Code? He talks about the prime meridian going through Paris is the Rose Line. And there's a Rosslyn Chapel that's named after it and all this stuff. And it's supposed to be the line of the blood of Christ, the children, the descendants of Christ. Except for it's all made up. The prime meridian is not called the Rose Line anywhere. So I want to bring that out in case. I mean, I was a little disappointed that was just absolute fabrication. I was thinking, yeah, maybe it's called no, not the Rose Line. So that's a picture of the prime meridian. That's where we measure zero longitude from. And then we measure east or west from that line. And it's going through the Royal Observatory in Greenwich, England. This here almost seems out of place. It's called a Foucault pendulum. It's a lot easier to say French names if you don't look at the spelling. Foucault, Foucault. The Foucault pendulum is a pendulum that you probably have seen somewhere in a science museum. Pendula, they go back and forth because all pendula do, and they put little blocks up and the blocks periodically get knocked down. Have you guys seen one of those? Do you know why they knock down different blocks?
It's the earth rotates.
Okay, because the Earth rotates. What almost no one understands, I didn't understand this when I was in college, I'm a physics major, is that it doesn't do a complete circle in a day. I thought since the Earth does one rotation a day, the Foucault pendulum would do one rotation a day. And you can just measure the angle, and if it's 90 degrees, you've gone through a quarter of a day, and that's not so. Yes.
So the Foucault pendulum it's like a creating thing, or wait, I'm confused. I feel like I don't understand what that is.
The Foucault pendulum is a pendulum that's set up so that it swings freely. And because it swings freely, it can change its orientation as viewed from the Earth. And because the Earth is rotating, there are some laws of physics that make it so it slowly precesses. So the path that it's going back and forth on slowly changes. And that precession depends on what your latitude is. So different latitudes, it will do a different angle each day. But it's very easily explainable. Okay, very easily. It's very explainable by physics if the Earth is a globe that's rotating. So that if you didn't get to 4 lines of evidence for the Earth not being flat, the Foucault pendulum is one. Of course, if you talk to a flat earther, you know what they'll tell you? They'll tell you, but during a solar eclipse, the Foucault pendula have been observed to do some funny things. So clearly the entire behavior of the Foucault pendulum, which can be described with general physics, is just not correct. We don't know what's going on with a pendulum. We don't know why the pendulum changes because there is an anomaly that has been observed during eclipses. There's a lot of explanations. I was reading up on that in preparation for today's lecture. No one is sure if there really is a change or not, but it seems that there is something weird that occurs during an eclipse. And it's not just with the Foucault pendulum, it's with a lot of gravitational things. And so it's something that really merits more study, try to figure out what in the world's going on. One explanation I saw was, well, when you have an eclipse, you'll have a sudden change in temperature. That change in temperature will cause a shift. One of the experiments that was done was in an underground mine that shouldn't have the temperature changing and still had a difference in their measurement. But the Foucault pendulum is a sign that the Earth is rotated. It's a ball Earth. That seemed out of place to me, but it was in there, and I figured let's go with it because it's interesting. Seasons. To everything, turn, there's a season. Anybody know when summer is going to end?
The exact date, is that what you're wondering?
Yeah.
September 21.
Okay, September 21? Yeah, did you look it up or you looked up there? It's typically September 22, which is my mom's birthday. So I just say, mom's birthday, that's the end of summer. It varies a little bit because the calendar varies a little bit, as we've talked about. That's why we have the leap dates and whatnot. But it's somewhere in the ballpark, September 21, September 22. That's when the summer ends and autumn begins. Now, Alwan did have to do some interpretation. It does not say summer ends. It just says autumnal equinox. The equinox is the time when, in theory, the hours of sunlight are exactly matched by the hours of darkness. I said in theory because there's a lot of things that make it so it's not actually that. First thing, really surprising thing. How much of the Earth is receiving sunlight at any given time? It would seem like half, because if you take a sphere, such as my little sphere here, you see half of it, right? The other half is blocked from you. If you're the sun's shining on the part you see. But there's a little physics going on. That physics is the Earth has an atmosphere. And when light goes into the atmosphere, it bends. We call that refraction. And so light from the sun will come like this and then bend in toward the Earth when it comes into the atmosphere. So what that means is light that would have come here and skimmed through the atmosphere but not hit the Earth, bends in and hits the Earth so that more than half of the Earth is lit up at any one time. Which means that you should have a little bit more daylight hours than nighttime hours, typically, on the equinox. The autumnal equinox occurs when, do you remember we talked about the vernal equinox before, and I said what makes it occur? Two vocab words combined. When the celestial equator and the ecliptic cross. So it's a specific place on the celestial sphere. We can look on here and we can find where they cross, which would be, I think it's right here. No, right here. It's called here the first point of Aries. And then we're going to have the other one over here. It doesn't even have a name on that one. But those are the two equinoxes, the places where we have the ecliptic crossing the celestial equator. We also have the solstices. The winter solstice says December 21, once again, usually around December 21, 22. Summer solstice, June 21, somewhere in that ballpark. Those are when the tilted Earth is either, let's say that Clayton is the sun. So if we have the pole of the Earth point as far away from Clayton as we can, then that's going to be our winter solstice. Half a year later, when the point of the Earth is as close to the point of Clayton as can, that's the summer solstice. So the solstices, as well as the equinox, okay, I don't know how to say the plural equinox, they both occur because the Earth is tilted 23.5 degrees roughly. And so as it orbits around the sun, that tilt stays the same. And you're going to have, if this is the Earth, or yes, this will now be the sun and this will be the Earth, tilted like this, the lower hemisphere of the Earth would be getting a lot more sunlight. Hence, that's going to be summertime for them. You come around like this, now everybody's getting the same. Come around like this, now the northern part's getting more sunlight, summer for them. So the seasons have everything to do with the Earth's tilt and orbit around the sun. Nothing to do with what a lot of people coming into this class believe. They think that it has to do with how close the Earth is to the sun. We're the closest to the sun in January. If the seasons were because of how close we are to the sun, January would be the hottest time. But that's not it. So why is it hotter during the summer and colder during the winter? There are a couple different pieces that come into it, but this is the primary one. During the summertime, the sun is higher in the sky, which means that you're getting more direct sunlight instead of the sunlight coming at a glancing angle. Now, we don't think about this much, but remember, we are at a latitude of 40 degrees. Okay. Actually, I'm going to do this. A white or a black screen. I'm not sure why it didn't give me a choice, but black will have to do. Here's the Earth. If the Earth is on an axis like this, and so you're going around like this, if the sun is shining light like this region here has direct sunlight, right? The sunlight is coming straight down on it. It's going to be getting the most. Up here, we're 40 degrees north. And then the Earth is tilted 23.5 degrees. What's the angle between my zenith at 40 degrees north and the sun? Yeah, that's 63.5 degrees. That's a pretty big number, but it's even more impressive if you say, how high then is the sun above the horizon? What's the angle between my zenith and the horizon? 90. So if I take 90 minus 63.5, by the way, that stands out much better on my tablet than it does on the screen. 90 minus 63.5, that's 26.5 degrees. How high is 23.5 degrees? 23.5 degrees is an angle like that. So the sun highest, okay, I'm pointing north now. The sun's not in the north, right? It's south. But the highest the sun is in the middle of the winter is at that angle. That's not very high. And so we're getting very glancing sunlight in the middle of the winter, which makes it not very much sunlight energy we're receiving per unit area of the Earth. If it was pointing directly like this, we'd get much more energy than if it's glancing like this. Second, the sun, the days are short. That is, the sunlight part of the day is short in the middle of the winter. And I'll show another picture to illustrate why. So you're getting less direct sunlight, so less radiation from the sun when it's in the sky, and you're getting that radiation for less time. So less light per hour and less hours of sunlight per day means you're getting a lot less radiation in the winter. Hence, the Earth doesn't heat up as much from the sun. If it doesn't receive as much heat from the sun, it's still giving off energy and cooling, it gets colder. Going back to the regular view here, this view. If we have the winter solstice is December 21, when should the coldest time of year be? What month? Not December, even though December, I mean, you would just think naturally, well, you're getting the least heating right there in December 21. Shouldn't that be the coldest day? It's not. January is colder, and February is usually when you have the coldest. Depends on where you are. And so the question is, why is it delayed? It's delayed because the Earth is cooling if it's receiving less heat coming in than it's giving off. And when the heat is at a minimum coming in, it's giving off more. But even as the heat starts coming, the heat that we're receiving starts going up, it can still be less than the amount we're giving off. And so you're still cooling because you're still giving off more heat than you're receiving. And so there's a bit of a delay factor. Yeah? Use my credit card, the one that's in my name. Yes, I gave some credit card in my name. I know, that's crazy. Really crazy. So there's a delay for the coldest month. Likewise, the hottest day of the year is not June 21. It's going to come mid to late July probably, because you're receiving more heat than you're giving off even for a while after you reach the highest received heat day. Okay, now back to this. I illustrated that this is for our location actually right about 26 degrees, right? Well, what about if it's the middle of the summer? So let's look at a similar picture, but now it's the middle of the summer. It's supposed to have an option of a white screen, which I far prefer. I'm going to at least change the color of my ink so it stands out better. This is going to really stand out. So the middle of the summer, here's the Earth still rotating around about this axis. Now the sun is giving off its radiation like this. Here's the equator. Here we are at 40 degrees north. That's a 40. And the sunlight is coming from 23.5 degrees north now, because the sun's as high as it can get. And so what's the angle between 23.5 and 40 degrees? How big is this angle? 16.5 degrees. So then there's only 16.5 degrees between the zenith and the angle of the sun. It's pretty close to overhead. So we're getting much more direct sunlight for a much longer period of time. Hence, you're getting a lot more heating and warming up. Yes?
So, why is it that Antarctica is cold pretty much all the time?
Cold pretty much all the time, very true. Cold and colder and coldest, though, it goes through variation, quite a significant variation.
Does it have to do with its location?
Yeah. So let's these pictures illustrate what I just did. Let's talk about that a little bit. Here's a nice picture. I have two of these pictures, one for Northern Hemisphere summer, one for Northern Hemisphere winter. Note here that this is the second one we did, where the sun for us is going to be only about 16.5 degrees from overhead. You have the center of those three sunlight rays comes to a line, and that line has a 90-degree angle between any line drawn on the surface of the earth and the sunlight. So the sunlight is at the zenith on this line. Since the sunlight at the summer solstice is 23.5 degrees north of the equator, then what would the latitude be for that location? At what latitude would you be if the sun is at 23.5 degrees north and it's at your zenith? Not the equator. I started by saying that latitude and declination are exactly the same because the declination of your zenith is exactly your latitude, always. And so if the sun is at a declination of 23.5 degrees, that is, your latitude is 23.5 degrees, for the sun to be at your zenith, then it's a 23.5 degree. I've messed up all the words. Let's just stay with the idea. This line is at 23.5 degrees north latitude, the highest point where the sun is directly overhead. Why? Because the earth is tilted 23.5 degrees. And so we call that the Tropic of Cancer. The Tropic of Cancer is the line that's the farthest north where the sun will at some time during the year be directly overhead. Now, if I go to the next picture, during the wintertime, the sun is directly overhead down here. What's the latitude there? 23.5 degrees south latitude. And that's the Tropic of Capricorn. So the two tropic lines are defined as 23.5 degrees north, 23.5 degrees south. The two locations, they're the farthest from the equator where the sun will at some point be overhead. Everywhere between those two tropics, we generally call them the tropics. At some point during the day, during the year, actually 2 points during the year, you can have the sun directly overhead. And so the tropics are the places where you have the most direct sunlight throughout the year because the sun will pass directly over. So you tend to get the most heating at the tropics, hence warmer, right? Most heating, warmer. Makes perfect sense there. But we don't just have the tropics. We also have this line here that's the Arctic Circle. This is the divider for where the sun is hitting. And so the place where you have the sun hitting here, notice it's not at the Earth's axis, it's shifted by this 23.5 degrees or tilt. And so the Arctic Circle is marking out the circle for where you're going to go at least one period of rotation without the sun ever setting. So if you live up there in the Arctic Circle, you're going to have the sun set, and you wait 24 hours, it still hasn't set. You wait another 24, it still hasn't set. If you live at the pole, you're going to be waiting for a long time for the sun to set. But of course, if you look at the bottom there, we have the Antarctic Circle, and what do you notice for all of the Earth that is beyond, that is in the Antarctic Circle here? It's all in shadow. It's receiving no sunlight. Now let's think about this. Receiving no sunlight for a few months. How much heat are you absorbing? None. But you're still giving off heat, so what's the temperature going to do? Drop. And so during the long night, it's really going to get cold. And even during the long day, the sunlight's still really glancing up there. And so it doesn't receive that much heat. Now, it's not that bad. I mean, I spent the summer acting up in Skagway, which is somewhere around here. I can't really tell. I don't have enough detail in my brain. The sun did set. It was down for about 2 hours on our shortest day. It was kind of like twilight. It never was dark enough to not see. In fact, one night, a buddy and I went out for a hike after we finished our play, we went out for a hike. We hiked for like 4 hours. It was sunlight when we left. It was sunlight when we came back. The middle of the night was in between, but we never had a problem seeing because it's just kind of like twilight. So all of this action is caused because of the Earth's tilt, which I think is really interesting. I hope you do too, because that's why we're in astronomy. We think this stuff is cool and fun and interesting. I've talked about this one, the difference in a solar day and a sidereal day. Remember I talked about the difference is because in the time it takes to do one rotation for the Earth, it's moved approximately 1 degree. Why 1 degree? Well, it's 360 degrees in a circle because the degree is approximately how much the Earth moves in a day. And so the Earth has to rotate 361 degrees to go from noon to noon. Hence, it's a little bit longer to do 361 degrees than it is to go to 360 for one rotation. So the sidereal day, or sidereal, if you were to break it up into two words that it's not, it's not side and real put together, just for a second. The sidereal day is shorter by a few minutes because you're doing 360 degrees of rotation for the sidereal day, about 361 degrees of rotation for the mean solar day. Now, the dateline has nothing to do with the place you call to find somebody to go out Saturday night. The international dateline is obviously a kind of artificial line. It's not a straight line. Now I want to say rose line because I told you it wasn't. The prime meridian, which goes basically, if that was a straight line, it would be something in that ballpark. So that's the prime meridian. Goes through England, and 1/2 of the Earth's rotation away, so that would be, let's change it to degrees, 360 degrees in a circle, so 180 degrees away, is where we have the international date line. And the international date line is where we separate and say, today is Wednesday, today is Thursday, today is Wednesday, today is Thursday. The time on the clock is the same, or maybe it's changed by an hour, like when you cross a time zone. But the time on the calendar changes by a day. Causes a lot of consternation, especially if you're a Seventh-day Adventist. It's hard for me to figure out exactly which island it is, mostly because it's not shown. But I think it's like American Samoa and something else are basically right on the international date line. What was that?
It's American Samoa. My roommate was from Samoa.
Okay. And so you have a situation like it's Sabbath here and Sunday here. What day do we keep? I go to New Zealand or something. It changes. And so that is the one place on earth where Seventh-day Adventists actually worship on Sunday on the calendar. And it's because there's confusion about what day is truly Saturday when you're on the date line. And it becomes clear it's kind of contrived how we decide where we're going to start the day. And they have a lot of consternation because you want to honor the creation. And so they sat down, how is it consistent? Did a lot of thinking. I don't know what went into it. So the international date line is where you change. Also very cool when you're taking flights. For my first wedding anniversary, my wife and I were starting out in Indonesia, and then we flew to the United States. So we started off, we flew from Indonesia, which we were, I think, right. Is that right? Somewhere around here. You can't tell my color. That's the problem. I will get better at this as time progresses. So we went, from here, we went up to something like this and then across. It's a long flight, but we crossed that international date line. And so we got up in the morning here on May 25 or 27. Wow, that's good. May 27. And then we were flying in the air and we landed here May 27. 30 hours later. So we had an extra long first anniversary. I thought that was very cool because we crossed the international date line in the middle of the night. So that's the purpose of it. Where is it located? 180 degrees from the prime meridian, roughly speaking. Stonehenge. You recognize Stonehenge, right? Has anyone here been to Stonehenge? I will someday. For now, I have to settle with I've been to Carhenge. Anyone been to Carhenge? Oh, goodness, people, you live in Nebraska. Carhenge. Western Nebraska. It's really not exciting. It's so not exciting that the people who owned it were trying to give it away and nobody would take it. But Stonehenge is really interesting. Stonehenge is believed to be essentially an ancient calendar. They have uncovered what appears to be incontrovertible evidence that it was designed so that on like the winter solstice, the sun rises on this rock lined up with these holes. And you have a number of other things that indicate that it was used for observation. You also have lots of bones that indicates it was used for burial. Examination of those bones suggests that they were burying people who came from large distances away. It wasn't just a local thing. A lot of mystery with it, but it's very cool that we have things like this to show that back then the Celts were definitely paying attention to the signs and the seasons, and they understood these patterns we're learning about. They understood that at that solstice, that's when things were going to start heating up again. Now, the temperature wouldn't be rising immediately, but you'd be getting more sunlight and so on. And it's not, of course, just the Celtics. You also have many other ancient cultures, like the pyramids have things that were lined up with what was the North Star at that time, and lots of things like that. The Mayans have theirs. Let's talk about the lunar phases. A month. A month is one lunar cycle going from new moon to new moon. What is a new moon? It's when the moon is completely dark. Now, flat earthers have some weird beliefs. I don't know how they believe the moon goes through cycles, but they do believe that the moon is giving off its own light. So apparently the moon is just getting light and getting dark. I don't know. The way the rest of us understand things is the moon is a reflector of the sun's light. It's a very poor reflector. It reflects somewhere around 7% of the sun's light, but the sun's really bright. And the moon's relatively close to us. And so only the part of the moon that's facing the sun is going to be lit up. So in every single picture here, only pay attention to the things inside here. The rest are illustrative of what it looks like from Earth. But on this circle, in every picture, the same half of the moon, that is the half on your right, is lit up. Because the sun's what's lighting it up. But since we're on the Earth, we're going to view it differently. So when the moon is roughly between the sun and the Earth, we see the side that's not lit up. That's the new moon. As it comes around, we start seeing, if you look in this orientation here, now I need to change colors again because that one didn't cut it. Yellow is going to work for me. If we look at it here, what we're seeing of the moon is that portion. So only the far right edge is reflecting light. And so that's what gives us this picture. The far right edge is reflecting light, and that's a crescent moon. We call it a waxing crescent. Waxing means growing. So it's a growing crescent. Which side of the crescent is glowing? Not growing, glowing. The right side. So when it's a waxing moon, it's always going to be the right side. Now you say, how do you know it's the right side, not the left side? Well, the moon is always going to be on the south side of us here because we're 40 degrees north latitude. So if you orient yourself so you're facing south, which you can always determine simply by how much do I have to raise my head? If I have to look back behind me, then I must be facing the other direction. So just look at the moon so you don't have to bend back behind you. If you're in the northern hemisphere, then it's going to be the right-hand side that the sun's on if it's waxing. Now, as we keep going around, when the moon is at a right angle to the sunlight, then we see the half moon lit up, and we call that first quarter. Keep going, and we're going to see more than half of it lit up, and we call it a waxing gibbous. Waxing, still growing. Gibbous, pregnant, more than half. And then when it's opposite the sun, it's a full. Keep going around, it's going to start diminishing. So we call that waning. So we'll go through a waning gibbous. The third quarter, those first quarter half would be second quarter, third quarter, and then new you start over. And finally, the waning crescent. A simple mnemonic to help keep things straight is dog. Not sure what happened there. If it is a full curve on the right-hand side, like you see for capital D, then it's going to be a waxing phase. If it looks like a big circle, then it's full. It's shocking. And if the curve is on the left-hand side, like in a capital G, then it's a waning phase. That works perfectly where? Northern hemisphere. Fortunately, over 80% of all humans live in the northern hemisphere, so that works perfectly for over 80% of all humans. If you're in the southern hemisphere, you're naturally going to turn north to view the moon. And so then it reverses everything. And so it's God in the southern hemisphere for the same idea. The seasons likewise are reversed in the southern hemisphere because when you're getting direct sunlight in the northern hemisphere, it's very glancing in the southern and vice versa. So we have Christmas in the middle of winter in the northern hemisphere. If we were in Australia, we'd have Christmas in the middle of summer because it's still coming in December, and that's the middle of summer there. Okay, it's the start of summer. I have to get on this. I only have 5 minutes left, so I might as well. Christmas. What is the origin of Christmas? Okay, so it's Saint Nicholas. What were you going to say, Mary?
It was a very secular holiday to begin with.
Very secular holiday to begin with.
I heard it was like a. I was gonna say, this at least what my teacher told me in public school, that it's like kind of like a pagan kind of thing.
Yeah.
That we just kind of continued it.
So, at Seventh Day Adventists, we pay a lot of attention to these things.
Mm-hmm.
Christmas, Easter, those are not Christian holidays originally. Christmas was a rebirth time because the sun has been going away, and now it's starting to come back again. And so Christmas originally was a pagan celebration of the winter solstice. And because of drift in the calendar, it's moved so that Christmas is a few days different from that. The new year is also supposed to be the beginning of the sun's rise. So New Year's and Christmas Day are really supposed to be the same thing. And then we have one more thing that some people celebrate now, the actual winter solstice, what they call Festivus, to celebrate the winter solstice. Those really are 3 different names for what fundamentally is supposed to be the same holiday. But because of shifting calendars, we have them appearing at different days. And it's, go back to Constantine, who wanted to Christianize the world, that took the pagan holidays and gave them Christian meanings. And so we have Christianized holidays. Easter is the vernal equinox, which is when you start to have plants starting to grow a lot, and so the fertility is what's being celebrated there for Easter. Okay, last thing for today is going to be tides. What causes the earth? You guys know the earth has high tides and low tides, right? The oceans do. What causes those? It's the gravitational pull, primarily of the moon. The sun pulls us a lot harder than the moon does. So it's not the strength of the gravitational pull. Remember, gravitational force was G m1 m2 over r squared. So how is it that the weaker one is doing the bigger thing? Okay, because it's closer, the variation is bigger. The tidal forces are the difference in gravitational pull from one side to the other. So if you look at the upper picture, the red arrows are very exaggerated, showing how strong the gravitational pull is for a little segment of equal mass on different parts of the Earth. And it's stronger on the side closer to the moon and weaker on the side farther from the moon. Now, the Earth has a very easy-to-flow fluid on its surface, water. And so that water, the water that's closer to the moon, is pulled harder than the Earth is on average, so it gets pulled away from the Earth, making it elongate. On the other side, the water is not being pulled as hard as the Earth, and so it elongates away because the Earth is being pulled away from it more than this water is. So the water elongates. Now, it's not just that simple, because the Earth is rotating. Because the Earth is rotating, those tides rotate with the Earth. And so the high tide is actually a little bit ahead of the moon because of the Earth's rotation pulling the water. And that makes something even more interesting. Because the high tide is a little ahead of the moon is actually pulled forward a little bit by that high tide. If the moon is pulled forward a little bit, it gets a little more energy. It's kind of like if I push on, he starts moving and has more energy. Remember that kinetic energy? And so the moon is slowly getting more kinetic energy from the Earth. And as it gets more kinetic energy, it's slowly orbiting a little farther away. Because remember, that circular orbit had to do with the radius. If it has a little more velocity, it's got to go to a little higher radius to do a circular orbit. And so the moon is moving away from the Earth at about a quarter inch a year, I think it is, because of that transfer due to the tides. And those tides can be really exaggerated by resonance. The highest variation between high tide and low tide is in the Bay of Fundy here, and you can see that's a pretty extreme difference. And that's just the difference in, 6 hours, because we have 2 high tides a day, one on either side of the Earth. We're out of time. I'll see you on Friday. Yo. And I forgot to press stuff.